Hello, I'm Bill Poirier,
I'm Ken Wharton.
and what we're going to do is have a little discussion about some of the topics that you heard earlier during our presentations. I'm going to, for purposes of this discussion, take one viewpoint, and Ken is going to take a different one. For the record, I'm a quantum agnostic. I don't hold any dogmatic beliefs, but for purposes of this discussion, I will take the many worlds viewpoint, and we'll see where that goes.
Very good.
So there were a few topics we're going to discuss. The first thing we wanted to do was to try to define terms. And already this led to a huge debate before we even started this, so I'm not sure we're going to agree on terms. But the first term is, what do we mean by an observer versus an interactor? So these were terms that we heard during Ken's talk. More or less, why don't you go ahead and...
Well, as I described it roughly, an interaction or an interactor is treated continuously in the mathematics. It's two things smoothly interacting, while at least in the formalism of quantum theory, an observer comes along and ends up with more discrete possibilities. You can get A or B, but not anything in between. And so I think the continuous versus discrete is a reasonable way to draw the line between interactor and observer.
And I might phrase it slightly differently. I would say that an observer has the ability to collapse the wave function. An interactor does not.
If you believe in such things.
Well, right. So the second question to address is, what is realism? So this was another term we heard in Ken's talk. Ken, what is your...
Well, a certain type of realism I'm interested in is space-time realism, the idea that everything happens somewhere and some way. There's events in space and time, and anything else isn't real.
So, for example, configuration space, which we'll get into a little bit later on.
Would not be realism.
Would not be real.
But it could be a different kind. It could be configuration space realism. There are other kinds of realism, right. Certainly. Yes.
So, whereas in my view, realism means that all the particles have a definite position and momentum at every instant in time, somehow. So, this is more of a hidden variables kind of an idea. Okay, and then the final distinction, I think this one you didn't really have a dog in this fight, but I want to get back to this idea of wave versus particle, because we're going to be describing some experiments that seek to determine whether an object moves, propagates, as a wave or a particle. But this is somewhat different meaning of wave versus particle than what I presented in my presentation earlier. So in that context, a particle is something that's completely localized in space, and it happens, a particle, or an object, shall we say, behaves as a particle only when it's measured or observed. The rest of the time it behaves as a wave. So we're going to be talking about experiments that are where the particle is actually only detected at the end of the experiment. So from my perspective, it's always behaving as a wave throughout the course of the experiment until the very, very end. And so then in that context, we have two different types of wave-like propagations. One which is a particle-like wave propagation, where you have some kind of spread over space, but you don't have any interference effects, where interference is sort of a standard wave behavior. If, on the other hand, you have a wave that has two or more branches, and those branches then cross paths, then you have the possibility for interference effects, and that's more of a wave-like wave. So apologies if that's over-confusing, but anyway, this is more or less what we mean by our terms. So why don't we start with the double slit experiment, classic quantum experiment going way back, and why don't you defend your position, explain what's going on.
Well, first let's set up the experiment. So you can send a single particle through a pair of slits, and according to the rules of quantum mechanics, this particle acts like a wave, and waves will go through both slits, and the two sets of trajectories will interfere with themselves. As you talked about the overlap, the high points of the wave crests add up. If you have opposite wave crests, they cancel, and you get this interference pattern on the other side. Interestingly, when you look, you don't see an interference pattern. You see a single particle, because you just send a single particle through the slits. But if you put up a screen and do the experiment over and over and over again, eventually that interference pattern builds up. And so now the question is, how do you interpret this? You are seeing individual particles sent through these slits one at a time, and collectively, they look like each one of them has gone through both slits. And so now let's get to the question of, well, how do we tackle this experiment?
So do you want to give an interpretation first, or shall we?
No, why don't you go first?
Okay. All right. So this isn't quite a many worlds interpretation, or it doesn't have to be necessarily, but in my interpretation, the measurement device itself is part of the quantum system, and therefore it is described.
The screen is part of that you're measuring the particles on is part of the quantum system.
And there, well, if there's an observer that detects which slit the particle went through, that observer is part of the quantum system. But let's start with the case where there's no observer.
Okay.
So there's no debate.
There's a screen.
There's a screen, but apart from that, there's no, prior to the final collapse, there's no observer. So we have two slits here. I'll try to do this with my hands if it comes through.
We have a board.
Yeah, I want to use my hands.
Okay.
So we have the source here. We have, my fingers represent different parts of the wave. My hands represent two branches. So we have one branch headed left, one headed right, and they reach the slits. The left branch reaches the left slit, and the right branch reaches the right slit. And then they come in together and merge on the far side where the detection screen is. Now, because these parts of the wave are all close together when they reach the screen at the end, they're allowed to interact with each other, and this is what gives rise to quantum wave interference. So that's the description. It's simple and straightforward enough in the interpretation that I'm going to adopt. Where things get interesting is where we add an observer. So
wait. Before we add the observer, let's finish the experiment. So you have this wave interfering on the screen, and then what happens?
Well, then, of course, you have a statistical distribution of where the particles appear when you measure.
Okay, so what's happening there? You have this wave, and suddenly now, instead of seeing a wave, you see a dot. Okay,
right.
so what's
happening?
What's happening?
You have collapse of the wave.
Okay, so the wave collapses to a point. Okay.
Right. So, okay, and then of course you do this over and over again, and then statistically the pattern emerges. Okay, so now let's imagine that we're going to observe which slit the particle went through. So the observer, we can think of, as in my presentation earlier, as being an inanimate classical measuring device. So a dial with a needle, and the needle position then represents the state of the measurement device. So we have these pieces of the wave that approach the slits. We reach the slits, and then at that instant, a measurement happens, and so the state of the measurement device becomes correlated with the state of the particle. So what that means is, if I take the z, the vertical direction, as the corresponding to the position of the needle on the dial, the measurement device, then this happens. Now, the scale in the vertical direction is very large, centimeters as opposed to nanometers. So now, no matter what happens, this part of the wave and this branch of the wave, they're never going to hook up. They go through, they meet at the middle, but they don't really meet because there's this big gap in the vertical direction now. And so because they're not close, they can't interact, and you don't have quantum effects, no interference fringes. So this is what happens when you treat, this is the interpretation, what comes out of that interpretation in terms of what's going on in the double slit experiment for the two possibilities.
Well, if a baseball flies near my head, if it hits me in the head, I become correlated with the baseball. And if it doesn't hit me in the head, I don't become correlated with the baseball. But we don't treat those two things as both happening somehow together. We treat either one happens or the other. There's still correlation, but we don't have to treat them both as if they're really happening. Why are you treating both of these events as if they're both real, as if it's measured over here and measured over here?
Well, that's what happens when you make the measurement device part of the quantum system.
This is what the rules of quantum mechanics tell you to do.
This is what the rules of quantum mechanics tell you to do. Exactly.
Okay.
So, your interpretation.
Well, why do the rules of quantum mechanics tell us to do that? Is because when we don't look, we see strong evidence is going through both slits. So, or when we look at it, I should say, when we look in a different way. When we put a screen there, we see evidence that something went through both slits. When we take the screen away, we don't see that evidence. If we do your measurement, your second measurement, we see evidence it went through one slit. But we say, but in this other case, it went through two. So therefore, it really has got to go through two, and that pushes you toward this both paths are real logic. The other way to think about it, though, is as a constraint problem where you have to now start to think about space and time altogether. And so in the past, the particles heading for these slits, And now you have different choices in the future. You could put a screen there, or you could do the second measurement, put observers there and see which slit it goes through. And we just assume that whatever's happening in the slits is independent of what's happening on the other side, whether the screen is there or whether the two detectors are there. But if it's not independent, I mean, it does seem like it's not, because every time the screen is there, it looks like it went through two slits. Every time a detector is there, it looks like it went through one. And maybe that's not just an apparent correlation. Maybe that's a true correlation. Maybe, depending on how you're going to look at it, the solution through the slits is different. Maybe it really does go through two in one case and really does go through one in the other.
Certainly is a distinct possibility.
Okay.
So now let's move on to a more interesting and weirder type of experiment, the quantum eraser experiment.
Okay,
So do you want
good.
to set this one up?
Well, let's start with the same framework. So now the idea is you wait until after the wave has passed through these slits before you decide what experiment to do. Do you set up a screen, or do you set up the detectors on each slit? And the idea is you randomly choose this after the wave has passed through the slits. And ideally, you imagine, it must have decided by now. Did it go through one or two? And so now you can try to test my approach by saying, now it must have committed to one or the other. And depending on which measurement you make, you get different answers. You get, it went through two or it went through one. And so I guess the delayed choice is you just wait to make that decision until after it's passed through the slits.
Are we discussing delayed choice or quantum eraser?
Okay. Well, now we can do quantum eraser. So, okay, go ahead and set up quantum eraser.
Okay, so rather than set it up, I'll just explain how it works in this picture that we've developed, because we have actually kind of limited time. So the idea of a quantum eraser in general is that a measurement happens, but then the information gets lost somehow. So then there's an interesting question. Does that mean that the past history never happened, or that it did happen, but you can't know it? But let me explain anyhow how this plays out in this picture that I've been discussing. So again, double slit apparatus. We start out at a common source, two branches of the wave, one to the left, one to the right. At that point, or perhaps even a bit later, we measure to see which slit we went through. And the measuring device has a definite setting that is one way for one slit and the other for the other slit. But it's perfectly correlated with what the particle is doing. So now a recording has been made. And then things propagate a bit further, and if I didn't do anything else, it would be exactly the same situation as I described earlier. But now the new wrinkle is we're going to erase the past. We're going to get rid of the information on the measuring device, set it back to its original setting, which was the neutral setting prior to making a measurement. And it's very important here that nobody has actually looked at the measuring device.
And there's no possible way to extract.
Yeah, there's no possible way to extract that information.
Right.
So if so, you've got to erase the memory of every device or every person that has observed what's happened. But assuming that you can do that, then what happens is you close the gap again. And so now your trajectories are close to each other, and now when they reach each other in the horizontal plane, which corresponds to the degrees of freedom of the particle, you have quantum interference because things are close. So that's a quantum eraser in this framework where the detector is part of the quantum system.
Okay. And that's certainly, I think, the best argument for treating the detector, at least very small detectors like atoms that you can, in practice, erase, treating them like a quantum system because of quantum eraser experiments that you can do in the lab, and you can basically kind of undo the measurement, and then it suddenly is back as if it looks like it went through both slits again. And that's, I think, probably the best argument for why should you treat this giant configuration space as being real. All these possibilities are somehow real. But I guess another way to look at it, especially if you're looking to what type of measurement is going to be made in the future, there is a type of measurement that you make it, erase it, and then make a different measurement. That itself is a measurement, right? And if you're solving this problem where the particle is constrained not only by what's at the bottom, but also what's at the top, then it knows the solution is constrained by the fact that there's an eraser up there waiting to erase it. Maybe in this case, the best way to think about what is a measurement at all is not an event that happens somewhere, but rather correlations, something that impose correlations between one part of space-time and another part of space-time. And if you have a screen there, that imposes a correlation because the screen is then correlated to the rest of the universe. If you have detectors there, that imposes a different correlation. If you have a quantum eraser where you measure it, erase it, and then measure something else, that's another correlation again. And so instead of thinking of measurements that have to happen somewhere in space and time, if we think of measurements as a train of correlations through space-time, I don't think quantum eraser experiments seem so strange anymore.
So the next topic on our list is the delayed choice quantum eraser, but I think actually it would be more interesting to talk about configurations.
Okay, let's talk about configurations.
This is what we mostly discussed offline. So there's a big difference in our interpretations or approaches here. In my approach, what matters is the positions of all the particles, what we call a configuration. And in quantum mechanics, most theories tell us that there are multiple configurations at the same time. Now, do they exist physically or not? That's a debate you can get into, but at least mathematically.
Let's get into it.
At least mathematically, they're there and they play a role.
Yes, right.
And you can pick one out and say there's only one that's right. The other ones aren't real, but they matter. To me, it's a very strange thing to say one of them is right, and the other ones, well, we just, they're part of the theoretical mathematical background, but they don't really exist. Why then do they take the form of other configurations? If configurations aren't what matter.
But we see that same mathematics in classical physics and statistical mechanics all the time. Anytime you don't know the full state of the system and you're interested in all the possible correlations, it's very natural to do classical statistical mechanics in this exact same configuration space you're talking about. And it's clear in that case that it's not a state of reality. It's a state of knowledge. It's a state of lack of knowledge. And you know this is correlated with that, but you don't know the details. You represent that in the configuration space. When you add one more node to your statistical mechanical system, you have to vastly increase the dimensionality of the math that you're using to analyze it in classical statistical mechanics. And the same math, the same explosion in dimensionality happens in quantum theory. But now all of a sudden we're treating these configurations as all real.
That's true, but I think there's one important difference. Well, two important differences. In statistical mechanics, as your state of knowledge increases, you can narrow the pool down arbitrarily.
Okay.
And you can't do that in quantum mechanics.
Didn't you just tell me that when you look, you suddenly collapse the wave function? What if that's not a physical collapse? What if that's an updating? I've just learned some new information, and now I'm going to winnow the pool down. It's
but
really
there's a limit to how far you can winnow in quantum mechanics, which doesn't appear to be the case in classical mechanics. The other very important difference, I think, is that in quantum mechanics, nearby configurations play a dynamical role. They influence how the real configuration, if there is a real configuration, how it changes over time. And in statistical mechanics, that's not the case at all. You have, if you like, these parallel trajectories, parallel configurations that don't influence each other at all. You're right, the mathematical space is the same, and that's kind of interesting and probably means something on a deep level. But these other two differences, I think, are quite
Let's zero in on those differences, though. In statistical mechanics, you have these spatial states of configuration space. And then you analyze them one way with statistics. And then to do dynamics, you keep mentioning dynamics, you plug them into some equations and see what happens next. Okay, so there's one style of logic. There's spatial statistical logic about the state. And then a different style of logic, dynamical logic, to evolve them. So there's two kinds of logic there. The sort of models that might save these weird quantum superpositions and entanglement and get them back into space-time are those that take the three-dimensional logic of StatMech and extend it to four. That instead of looking at a three-dimensional state statistically and then propagate it dynamically, what if you look at space, all the events in space and time, and treat that whole thing statistically? Don't have the dynamics in there. Just look at the statistics of events in space-time.
Interesting.
That way, you get out of some of these traps that force you into configuration spaces being real. And maybe it is real, but if you're going to get out of it, you need something weird like this four-dimensional perspective.
So maybe let me ask a more basic question. Why do you prefer the 3D physical space we're all familiar with to configuration space?
It's smaller. It's smaller.
Can't argue with that.
And I experience it. I mean, I like to think there's some reality to my measurements, and I'm not just some tiny cog in some vast structure that would make Occam roll over.
But you're
in his
not
grave.
just you. I mean, there's lots of yous.
If there are, we're all equally confused, perhaps. Or maybe there's one of me out there that is accepting of many worlds.
I think there probably
Okay.
is. Okay, so we're starting to run out of time. We've been asked to pose and answer some questions. Well, the answer is probably not. We probably cannot create reality with our conscious minds, but one has to be a little bit clear about what one means. It's certainly true that consciousness may play a role in observation in quantum physics. If it does, then the observer's chief role really is to just bring about wave function collapse. But the observer has no control whatsoever about what state is collapsed to. So this is maybe a misconception that some people might have. We can choose our reality. We definitely can't choose it. All we can do is force the act of choosing and then let the chips fall where they may.
I would say that very few, if any, people in the physics or philosophy of quantum theory would say consciousness per se is important to any of this. But I would also say that it's unclear what quantum reality means. It's very clear what space-time reality is, and so I'm not sure exactly what the question is asking.
All right, good answer. It's not clear whether or not consciousness is necessary for measurement per se. It may be. Certainly there were some very bright minds in the early days of quantum theory who thought so, people like John von Neumann and Eugene Wigner. But again, that begs the question, what is consciousness? So it's not clear whether consciousness is a prerequisite as an ability to collapse the wave function or not. In the many worlds interpretation, of course, it isn't. It plays no special role. There is no collapse of the wave function. The only collapse that occurs is apparent wave function collapse.
I think the reason people look to consciousness, and not people in the field, but maybe from looking at it from outside, see this interactor on one side that is continuous and an observer on the other side where you get discrete outcomes, say something special has to happen in the middle there, and maybe that special thing is consciousness. But I think there are many, many better answers, many, many better ideas of what's happening when you go from small systems to large systems, when large systems act as boundary constraints on their surroundings in a way that small systems don't. I don't think looking to consciousness is the right place to put in the dividing line between these two domains.
We're in complete agreement on that score,
Okay.
I think. So, okay, next question.
I made the point in my talk that when we look at something, we interact with it, right? But that's not always true. When Sherlock Holmes solved the mystery of the dog who didn't bark, he solved it because he didn't hear a signal. He solved it because he didn't hear a dog bark. And that allowed him to deduce something about reality. And that certainly happens anytime you're in a state of ignorance, that seeing an empty channel can inform your knowledge of a situation without any interaction. And so if you, by learning about something, can update your state of knowledge, which you should, anytime you learn about something, definitely update your state of knowledge, then that pushes you, I think, more into the viewpoint that these quantum states that are collapsing aren't real. They're states of knowledge. And when you learn something, then you update it without needing any interaction at all.
Okay, final question. I think the reason why you can't consider an atom as an observer of a photon has to do with how we defined observer at the beginning of this presentation. So we define an observer as something that can collapse a wave function. It's pretty clear that a subatomic particle interacting with another subatomic particle the two particles together have to be treated as the quantum system. In other words, one particle on its own does not have the ability to collapse the wave function of the other. So that's the reason why an atom cannot be considered an observer.
I disagree. I think that in certain circumstances, an atom, well, say you measure the atom next with an atom detector. So now you have this chain of correlations between what you're looking at, the photon, and this atom, and your bigger atom detector, and the rest of the universe. You have this chain of correlations that funnels through the atom. And I think in that case, you could treat the atom as an observer. But the key is, if you then didn't measure the atom, if you put it through one of these quantum eraser experiments, now there is no chain of correlation to the rest of the universe, and it doesn't count as an observation. And typically, I would say it doesn't. But in certain circumstances, I don't see why you couldn't have that atom be the forefront of some structure in space-time that eventually measures the photon.
We should also not forget that we started out with different ideas about what an observer is.
True.
So I think with that, we've come full circle.
OK, thanks.
Pleasure.